Good morning and welcome to the Q&A session 43 from the playlist of IIT-JEE Main Physics. The topic is how to find the power required to move a conductor in a magnetic field region. So based on this topic, I have one question which was asked in the IIT-JEE main exam in the year 2014. So this is the figure which was provided along with the question. And the question here is a conductor lies along the z-axis such that z is greater than equal to minus 1.5 and less than equal to 1.5. So we can say that the length of this conductor is equal to 3 meter. It carries a fixed current of 10 ampere in the negative z direction. So the direction of the current is shown here, and the magnitude of the current is equal to 10 ampere. For a field, that is for a magnetic field, B is equal to 3 into 10 to the power minus 4 into e to the power minus 2x j cap Tesla. The power required to move the conductor from origin to x is equal to 2 meter and y is equal to 0 in 5 into 10 to the power minus 3 seconds, assuming that the conductor moves parallel to the x-axis. Now here, the direction of the current is along the negative z direction. The direction of the magnetic field is along the y-axis. It is written here, that is B is equal to 3 into 10 to the power minus 4 into e to the power minus 2 is j cap. J cap means the direction of the magnetic field is along the y-axis. So by the right hand rule, the direction of the magnetic force will be along the x-axis. Now, force, the magnetic force F is equal to ILB sine theta, where theta is the angle between the direction of the magnetic field and the conductor length vector. So this theta will be equal to 90 degrees. So finally it will be equal to ILB. So here I is equal to 10, L is equal to 3 meter, I is equal to 10 ampere, and B is equal to 3 into 10 to the power minus 4 into e to the power minus 2x Tesla. Now we have to find the power in moving the conductor when the conductor moves from origin to x equal to 2 meters and y is equal to 0. So the power is equal to work done upon time. So simply now we have been given the time that the conductor moves from origin to x equal to 2 meter in 5 into 10 to the power minus 3 seconds. So power is equal to work done upon time. So simply we have to find the work done. Now for a very small displacement, work done is equal to f dx. So if I want to find the total work done in moving this conductor from origin to x is equal to 2 meter and y is equal to 0. So this will be equal to integration within the limits of 0 and 2 f dx. Now f is equal to ILB. So this is the equation which I have got, and here the total work done in moving the when the conductor moves from the origin to this point will be equal to I is equal to 10 into L is equal to 3 meter, B is equal to 3 into 10 to the power minus 4 into e to the power minus 2x dx. So we have got this equation now, and we have to simply solve this equation in order to find the total work done. Thereafter we will divide by this time, that is the time taken by the conductor to move from the origin to this point, which is equal to 5 into 10 to the power minus 3 seconds. So this work done will be equal to 9 into 10 to the power minus 3. 9 into 10 to the power minus 3 integration within the limits of 0 and 2 e to the power minus 2x dx. This is the work done. This is the total work done. Now power required in moving the conductor when the conductor moves from the origin to this point, that is x is equal to 2 and y is equal to 0 meter. So power will be equal to, that is power required will be equal to 9 into 10 to the power minus 3 integration within the limits of 0 and 2 e to the power minus 2x dx. divided by the time taken by this conductor to move from this point origin to x is equal to 2 meters and y is equal to 0 meter. This is equal to 5 into 10 to the power minus 3. So this will get cancelled out. So finally it will be 9 upon 5 integration within 0 to 2 e to the power minus 2x dx. This is the equation which we have got. Now by solving this, integration is very simple, so it doesn't need a lot of elaboration. So here simply you can substitute the value of minus 2x is equal to u. So by substituting you will get u is equal to minus 2x. So du upon dx will be equal to minus 2. So dx will be equal to du upon minus 2. Okay, and finally this integration will get converted into e to the power u divided by this minus 2. Okay, so if I solve this integration, this equation gets converted into 9 in bracket 1 minus e to the power minus 0.4. So I'm not elaborating the integration of this term because it is a very simple integration, so it can be easily done by you. But the integration of this, the entire value of this, the entire value of this that is 9 by 5 into the integration of this value will give you this value, and this will be equal to now. This is equal to 9 into, now this is equal to 1 minus e to the power minus 0.4. So this roughly works out to 0.33, and you will finally get this value as 2.97 watt. So here the correct answer will be the second option, B option here. That is the power required to move the conductor from origin to x equal to 2 meters and y is equal to 0 meter will be equal to 2.97 watt. So here the most important thing was that we have to first of all find the magnetic force, and thereafter we have to find the power by using the equation, that is power is equal to work done upon time. The total work done was calculated by integrating this value, that is f dx. F was equal to ILB dx within the limits of 0 and 2. So by finding the value of the total work done and by dividing the time taken by the conductor to move from the origin to x is equal to 2 meter and y is equal to 0 meter, we were able to find the value of the total power which is required to move the conductor from origin to this point. Thank you very much for joining this session now. In the next session, I will be continuing with the same chapter, that is, this is the question from the chapter of magnetic effect of current, or you can say the moving charges and magnetism. And I will be continuing with the same chapter, but the question will be different. It will be entirely different and will be based on a totally different concept. So till then, have a nice day. Bye.